Good afternoon, everyone. Thank you for coming to the stream. If you're here, I know it's a little bit odd. I usually do Sunday because Sunday usually works better for me. But as I mentioned last weekend, I'm going to be going on a work trip starting tomorrow. So I won't be able to stream tomorrow. I'll be in the air probably. So today, if my cat will stop shaking the desk, today we're going to get into converting our C-like language into assembly. So if you remember last time, we implemented all of the things that turn our kind of higher level language, which is Lisp-like, into something that looks like C semantics. So basically C semantics with gotos. You have sometimes called 3 address code type of intermediate representation, where you have a for every statement that's kind of an intermediate result, you have a variable that's being assigned to, and then 2 arguments probably. Anyway, what we're going to do is we're going to take our C-like language that we had just implemented loops in that language, and we're going to lower it into an assembly language with virtual registers. So variables, assembly language with variables is probably a better way to put it. And just this couple days ago, maybe yesterday, I forget, I saw a great blog post about register allocation. And there's some techniques that are not covered by Essentials of Compilation, which is what we're doing, that are really interesting, and they're called linear scan allocation. So our implementation does graph coloring, which is the classical way, and also is, I think, easy to understand from a high level, but the implementation of it was really kind of wonky. And I think the point of linear scan was also that it's difficult to design a register allocator for multiple architectures. And I think that the way that ours is implemented definitely shows that. It is very particular to x86. And that's partly because of calling conventions, callee versus caller save registers, as well as the numbers and types of registers that you have. So there's not really a general solution for doing this with graph coloring. Anyway, it's a really interesting blog post. I'll share that with the group if people are interested. Otherwise, let's get started. If you're just joining the stream for the first time, welcome. We are working through a book called Essentials of Compilation, which is, if we open this tab, oops, wrong one. It is a compiler's course for Indiana University, and it is also a textbook. And they keep the textbook up to date on their GitHub account. So we are following. This is going to be this version of the book is probably, I don't know, about 6 months old at this point. But we've got the PDF version of it, and we are implementing this book in Gleam rather than in Lisp, rather than in Racket. So there will be things that you'll see in our what am I trying to say? In our construction of this compiler that don't really match up. The main differences being Gleam has a, dare I say, Rust-like syntax with some things that look like OCaml or Elixir, and Lisp is Lisp. Also, Gleam has strong types, which has been at times a burden, but at other times a huge boon for us. especially when I'm going to add a new thing and I've changed the semantics of the intermediate representation, and then I have a whole bunch of new case expressions to fill out. Having the language server fill those out for me has been great. But so we will be kind of mentally translating things from Racket in the examples that they show in the book to Gleam. So if you're feeling any cognitive disconnect there, that's why. And we'll bear with it, and hopefully you'll see that the approach in Gleam is really nice, because Gleam is a nice language. So here we are. All right. So last time, we did explicate control. This phase is about, as I mentioned before, it's about turning our Lisp-like language into a C-like language, and you can see some comments that we left in a previous exercise where we're translating this let like thing into assignments. So that's the sort of thing that we'll be doing in this phase. So this phase of the compiler takes explicit or takes this sort of implicit stuff with scope and turns it into explicit sequencing. So we're going from things that are kind of lexical with a few escape hatches. Since we added loops, we need mutable variables for those to work. So instead of it being all lexically scoped, then we have imperative, and we just variables are at the global scope, essentially. Okay, so that's what this phase does. It turns things in different positions in the program into their constructs in the imperative language, which is defined by C loop. So this is the abstract syntax of that language. Okay. But what we were doing is we were writing tests. So last time we wrote this test, which was taking, this particular program and then passing it through our phase here and checking that the output matches what we expected, which it does. We got that test passing. But that was just a let with a mutable variable. We need to do some loops. And loops are a bit more complicated because they introduce a bunch of new blocks and identifiers. So let's go ahead and I think that this set bang was a new construct. But we're using setBang inside this begin. So I think that I'm satisfied with that, and we'll have to use it inside our while to make a useful program. So let's go ahead and write a program in our Lisp-like language. So let's do a let. And let's let x equal 5. Okay, and then we're going to do another let inside that with maybe we could use their example from the book. That would be good. They have a good example at the beginning of this. Not that one. Loops. Yeah, let's use this. This is good. Okay, and I'm going to get everything indented so that we can... Okay, so this program, and we're going to take all of the stuff that we did before. So we're going to send it through the passes that precede explicate control. So this program initializes a sum and then initializes the loop variable to 5. And it's basically going to add up add up the numbers from 1 to 5, essentially. So it's going 5, and then it's, you know, decrementing I on every pass. Okay, so what can we reasonably think that this is going to look like? So we're going to have a C program. This gets kind of complicated to conceive of, but we know that each program is going to have an empty info, which we use this later in later passes to store information about where variables are assigned and like what their conflicts are and so forth. But we also know this is going to have a list of blocks, and every one of these programs has a start block. So the question is, what is this start block contain? It contains a tail. And what is a tail in a C language? That is either it's a return, a goto, an if, or a sequence of statements. So this is how we do sequencing with like a cons-like cell. Okay, so we know there's going to be a start. This is the entry point for the program. So I think that what we're going to see is we are going to see a sequence, and that statement is going to be an assignment. So we're going to assign and let me split this out to the right so I can read it while we're looking at the program. Okay, so we're going to assign the variable, and one of the things that is happening in one of these passes, this uniquify, is it's adding suffixes to all our variables so that they, if they get shadowed, they get a new suffix. We don't have any shadowing in this program, so I think it's just going to be some .1, right? And that expression is going to be an atomic integer 0, right? And then inside there's going to be another sequence which is going to have inside it an assignment. And that's going to be I.2 probably. Atom C.int 5, right? Okay. So those are the assignments. And then there's a question of how do we represent this? And I think that what's going to happen, based on what we implemented last time, is that this begin is going to be replaced by a goto. And that goto is, that goto is going to be the beginning of the loop. So let's look real quick. Right, so our begin is in tail position here. What do we mean by tail position? Tail position is the return value of the program. So this begin wraps, or is in the last position of this expression. So it's going to, I'm sorry, it's this. It's going to be the return value of the program with the contents of this begin. The while, though, will just, the values that are returned from the while are thrown away. They have type void, but some has type integer, and that's fine to return from the program. So So we're good there. Right. So I think this is going to be, 2 assignments and then a goto. Okay. So the question is, what is the goto? What is the label of the goto? I think it's going to be like loop dot something. So this explicate tail on the result is returning a variable, like atomic variable, right? So C return atom variable that. This creates no new blocks. And then this goes through and does explicate effect. So this is the statements that precede the result or the last expression in the begin. Their values are just thrown away, right? So that's what they call effect position. It's you only execute these for their side effects. And so if we are looking at explicate effect, what I'm curious about is what will be generated in terms of the blocks. So let's kind of walk through it. So the first expression in here is the while loop. So we create a label loop and put it in the blocks. Or we create a label loop based on the blocks. Okay, and then the loop start is go to that label. Okay, so yeah, and the condition, so we create a block for the continuation. So this code generation is continuation passing style. The continuation on this while loop is going to be that return sum. So this does create a block for that. So this will be like block 1. And let's go to this function. Yeah, so we put an underscore between them. Okay, so if we're over here in our test, let's put a pause on this, and then we know there's going to be another block, which is block underscore 1, and that's going to have return sum.1 is what it's going to return. That's going to be the entirety of that block. And I've got a problem here, and then this is not wrapped in a list. Okay. So that's what's going to be generated here. And then the body of the loop is going to be in effect position. And its continuation is going to be, jump back into the loop. Okay, so the body of this, let's go look at what's in the body. The body of this is a begin. Okay, and then the last statement here, we're going to call explicate effect. So what we're doing is we're right here, this begin, and we're looking at this set expression. So we'll call explicate effect, and this is explicate assign. So it just calls explicate assign, setting this value to this variable, and the next, and passing through the continuation. So So if we go to explicate assign, then it's this is generating an assignment, right? So you can see c.sequence assign in the continuation in a lot of these places. And our program is going to be assigning the expression minus I1. So subtract 1 from I. So if we look at minus here, so this is going to give us, excuse me, right. Okay, so our oops. So let's go back to explicate effect. So we're looking at, that's what that set bang is going to do, and this is just going to loop over that, adding them on the front. Okay, so back in the while loop, it's looking like that's not going to create any blocks because there's no branching, right? There's no branching in any of that. It's just set this variable to this value, set this variable to this value. Okay, and then there's the loop condition. So we've generated the statement essentially after the while loop is the false branch of the condition, and the statement that is the body of the while loop is the if true. So now we explicate in the predicate position on the condition of the while loop. Okay, so if we go into explicate predicate, and our expression here is greater than I0. So this is going to have see what are we looking at. We have a comparison, right? So it's creating a block for if true. So I don't think that we did that before, and it's creating a block for if false, but the if false is should already be a goto. So that's not going to create a new block. So we need to create a new block for the loop, the body of the loop. So this is going to be block 2. And we don't know what's going to go there yet, but we'll fill that in. But there's also going to be loop. So note that this will have been, we're down here in explicate effect. It's created this label for loop before it creates the label for the exit block. So I think that this is actually going to be block 2. This is going to be loop 1. And we'll have block 3 for the body. And that block 3 is generated here in explicate predicate. And then it's inserting that entry point of the loop into the blocks that we've already accumulated, and you jump. Okay, so and you can see here, if we go back down, what I've been explaining, the decomposition of this expression into these different blocks with gotos, is basically this diagram. Your entry point is goto loop. You loop, you test your condition. The false branch goes to whatever follows the loop, and the true branch goes into the body of the loop with a jump to the loop condition again. So that's what we're trying to construct here. Okay, so this is the exit point right? This is the body of loop. This is the loop condition. So let's write the loop condition first. And I messed that up. Wrong language. I jump between so many different languages in my work that I get confused about which comment style we're using, right? Okay, so now we know that this is after you've assigned I, right? We want to go to loop 1. So that's the entry point of the loop in our program here. We have let sum 0, let I 5, and then the begin expression, which the very first thing it contains is while. So we should get a go to loop 1. Okay, so here's the loop condition, which will be a cif, and the expression has to be, I think it has to be a comparison. This is a, if I recall correctly, this was a compromise we made because technically this has to be a comparison operation. Although I suppose if you've already done a comparison operation and assigned it to a variable, which is Boolean, it's fine. Okay, so we are going to get, what's the comp type is brought in from L while. So we need L dot less than. Okay, and this is going to take an atomic, which is going to be variable I dot 2. Right? Or no, greater than. So we need greater than I dot 2 and integer 0. Okay, so that's our, that's beginning of our loop condition. So that's the check. Sorry about me fussing with the formatting here. I want to make, because we've got a lot of nesting, it's easy to get dizzy on that. And I want to make sure that I get that lined up in a way that makes sense. Okay, so if it's true, then we jump to block 2, right? And that's the other thing about ifs at this layer. They have to, their branches have to be gotos. And otherwise we go to, I'm sorry, no, this is block 3 is the body. Block 2 is the exit condition, the exit point. I'm gonna move that up because that's generated first. Okay, actually it's not, but whatever. All right, so now we need to do the body of the loop, which I think that we can figure out pretty quickly. So that's going to be set sum to sum plus 1 and set I to I minus 1. So we're going to have a sequence, and then it's going to jump to the loop. Okay, so sequence is a tail, so we're going to do assign. Okay, so assign, we are assigning to sum, and the expression is going to be a primitive of plus. Right? And that needs to take 2 atomic arguments, so we're going to use a variable sum.1 and an integer. No, it's also a variable. We're adding I, yeah. Okay, so that's the first expression in there, and then it's also going to do another assignment of I.2 to the primitive C dot minus C dot variable I.2 and integer 1. And then the final thing it's going to do is go to loop 1. Okay, I hope you all followed that. I feel like I barely followed that. But if we, let it format, good. So, and let me put these comments above the item because it's not leaving them on the end of the line. All right, so now what we're going to do is what we've done in so many of these tests before. We're going to say P1 or P and pass it to our pass, explicate control, should equal P2. So we're saying, you transform this program into this program via this pass. And let's find out if we did this right. If I had to guess, we're going to have things named differently. Okay, so we have a little bit of out of order on the block. So we have block 1 is the return. So I got that wrong. So it'll be block 1. Oh, right, because where's our block 2? We didn't do a block 2. This is block 2. Oh, interesting. So there's some explicate, or there's some removing complex operands going on here. So we have introduced a temporary variable to hold sum. I wonder if we have a bug, because those are not complex expressions or complex operands. Why would we introduce? Let's look at the original program. Now I could see introducing a new variable for this, but set doesn't need to have complex operands removed. Because what you can see going on here is we're assigning a temporary variable the value of another variable. But this is atomic. This is not. And the reason you do this is to make sure that all the arguments of primitive operations are atomic. They're either variables or literals. But we're introducing a temporary variable where we don't need one. Okay. Let's... I think that this is semantically correct. It's just wasteful, and we shouldn't be doing it. So we need to go look at what we were doing in remove complex operands and make sure that we're not introducing too much new cruft. Especially where these are all atomic expressions. in the condition and in this. So it's bizarre to me that that would happen. I think we have a bug somewhere. Regardless, okay, so let's look at block 2, which we know is going to be the body of the loop. So, you know, we thrown in a temporary variable there, and we've assigned another variable to it, and then we've assigned I to another temporary variable, and then we are assigning the value of those the plus of those two temporary variables. Okay, and then our next step is assign I2 back to, and maybe this has to do with get bang. I guess that's what this is like get bang. And maybe we have a problem there with that in remove complex operands. We may need to revisit that, because I think, I'm trying to remember which phase would it be. Yeah, we do uncover get here. And the whole point of that get bang thing is so that we can make sure that we capture the values of things that might be mutated. So maybe this is correct. Gosh, it just feels so wasteful. Partly because this, this order of things is being preserved here. Both of these are mutable, so this would be like get bang sum, get bang I, and this would be get bang I right there. But we're not in a context where those need to be sequenced with. Oh, do we need to be thinking about I guess it's just there to ensure that they're evaluated before they're used. Because something in between might mutate them. We're going to have to go back and look at that section, I think, today, because I feel like that we're missing something, and our compiler is doing something that it shouldn't need to in this context. What I don't know, what I'm not certain about, is whether just because it works in this context without the additional bindings means that it will, like, if we remove them from being generated here, if that will mean that they will not work in other contexts where the ordering of operation does matter. And we can look back at our other tests, because I think that we did in the remove complex operands, we were looking at the that example that's kind of pathological. And what happened was it needed to sequence the gets, the reads of variables, with reading from, so like the interference of side effects, not the existence of them, but like where they might conflict with one another. So I don't know how we resolve that. Anyway, let's continue to look at what the code we wrote said the program should be, and see if it still makes sense. Okay, Getting back on track. Okay, so then there's the assigning temp for value of I2. And then assigning I2 the value of temp 4 minus 1, and then go to loop 1. So we are getting this looking roughly correct, but with additional bindings. Okay, and then let's look at loop 1. Loop 1 is we have sequence of assign, and here again they're saying I2 is mutable, so it is getting an additional variable. Okay. And then it's comparing temp 1 to 0, and go to block 2 or go to block 1. Okay, so this makes sense. We don't have block 3. And the reason why this makes sense and they don't actually conflict is that we have a problem of we are not, and this is maybe okay, but note what we're doing here is we're creating the label for the for the entry point of the loop and the conditional before we create the block for it, because we need this label in order to generate the if true, right? Because it needs to jump to loop start. So we haven't inserted into blocks yet, so 2 of these things are going to get the suffix 1, and it just so happens that loop gets it and the false branch block gets it. That's why we have 1 1 2 rather than 1 2 3. Okay, so let's see here. Okay, so loop 1, oops, we assign that variable, we jump to block 2 or block 1. And the start is assign sum1 0, assign I2 5, go to loop 1. That's exactly what we expected for the start. And then we have the return in block 1. Okay, so we're still going to be wrong. If we run this test again, it's still not going to pass. I want to go back and look at remove complex operands at its test and see if there's something that we can revisit there, because I think it might be wrong, or at the very least it might be inefficient, and I think that's part of the issue here. Okay, so here's the get bang. And it really has to do with this atomic position, because if we have get bang here, we just pass it through. We don't introduce a new variable for it when it's in expression position. But when it's in atomic position, when would it be in atomic position? It would be there when it exists inside a primitive operation, right? So like if it's A or B here, or in comp, this is the example we have in our branches. Like, you've got to make sure that the operand, or not the operand, but the 2 operands in the comparison are both atomic. The question in my mind Yeah, I think this is fine. There's a possibility that there will be an optimization in the patch instructions phase where the like the variables that are capturing the that are capturing the same or capturing the variable that's mutable, so like the temporary variables, that they'll get assigned the same register. um, and then we'll get a move from, you know, this register to the same register, and that'll get called when we generate the code, because that's a pointless move. However, boy, it sure does feel wasteful, doesn't it? I was looking at this and thinking, okay, well, what are the circumstances um, where you have something like where the get bang the order matters, and I think like if you had a begin expression as the contents of one of the expressions inside a primitive operation. So like let's say you had plus, and A contains a begin and B contains get bang variable. When you evaluate A, it could, because you know this variable is mutable that's in B here, you could mutate the value before you evaluate the plus. So interestingly, what we're going to generate here is, maybe we just need to write an example for this to understand the, let's look at the complex operands test. Yeah, like there's this stuff, right? They are in the book saying that these get bangs get removed. But we know that by traversing the tree that y3 gets mutated and x2 gets mutated. The problem is that you want to make sure that this left hand side of this operation gets evaluated before this one. And of course this is the left hand side for this outer plus. Okay. So I think we, the hard part about this is looking at a single expression and knowing whether its side effects are going to order correctly with the outer expressions, and we can't know that without some crazy graph something, and that the book is not encouraging us to do that. Let me skim back through the section of remove complex operands again and see if we can glean anything new. And then I think that what we'll do is we'll declare defeat, introduce those temporary variables into our test, and move on, because I think it's, like I said, it's semantically correct. It's just inefficient. And those two things are not necessarily the same goal. Efficiency and correctness. Okay. So new language forms, get, bang, set, bang, begin, and while are all complex expressions. So this is why in a remove complex operands pass, they get, because they're complex expressions, they get bound to new variables. When they're in atom position. When they're in expression position, we just dig down into their contents, right? Okay. The sub-expressions of set, begin, and while are allowed to be complex, right? So obviously get, bang is just the variable. There's nothing new there. Set, bang, yeah, so they're saying these don't need to be atomic, right? So begin, its contents don't need to be atomic. Set, bang's contents don't need to be atomic, and neither do the while loops. Okay, when a complex expression appears in a grammar position that needs to be atomic, such as the argument of primitive operator, this is what we've been talking about, must introduce a temporary variable and bind it to the complex expression. This approach applies unchanged to the new language forms. Okay, so they're saying get, bang is a complex expression. It needs to be bound to a variable before it's used. That makes sense. Okay. For example, in the following code, there are two begin expressions appearing as arguments to the plus. The output of RCO expression is then shown, and this is where we had some disagreements with what was in the book based on our code. And there may yet be a bug in here. But, okay, the begin expressions have been bound to temporary variables. Recall that let expressions are allowed to have arbitrary expressions on the right-hand side. So it's find a place, begin there, right? So, and that's what why we got in our test here. You know, this let has, you know, a very complex expression inside of it. But bindings, it's fine. Because as we turn those into imperative assignments, you defer evaluation of this until you've got all of that, right? The continuation of the stuff inside here is assigning temp 1 and temp 2 to temp 3. Okay. So the thing that I'm noticing, though, is that this pass, or the thing that we may be doing that's different from the book, and I said before that this feels like it's not correct, because this is a flattening, whereas, you know, if it's allowed to have a let, then we should be doing it recursively, and so you'll have some like cascading stuff like this. But I think a difference that we could introduce, and it's going to blow up our test for sure, but when get, bang is in expression position and not atomic, we could convert this to atomic variable far. Because atomic is an expression. Or so. No, I'm looking at the wrong one. We need L while. L mon while. So like atomic, containing an atomic value is an expression. So in this expression position, where you're not trying to be atomic, it could, we could replace the get bang with this. Why don't we make this little change? The thing is that this is not, because this is the transformation itself. This is not going to change the meaning of get bang through the rest of the program. It's just going to say when we're in expression position, you don't need to have get bang. Because what we're doing here is in the atomic position, we're converting that get bang to an assignment to a temporary variable. Okay, so there's a problem here in that our explicate control test, PAT, is going to fail, but we're also going to get a failure in our remove complex operands test. So yeah. So whereas before I think we had get bang, now we're getting just the variable, which is more like, I think the structure hasn't changed, right? We're still introducing temporary variables in the same structure we did before. It's just that when it's in expression position, we don't need to keep the get bang. And honestly, when it's in atomic position, yeah, when it's in atomic position, it's just going to be the variable. Remember, that was not, like, this get bang is not a semantic change of what the intention is. It's just a signal to this phase that, hey, this variable is mutable, so it is essentially a complex expression, which means you need to, if you're in atomic position, you need to capture that into a new temporary variable before you use it. Okay. I don't know if I want to make this change right now because semantically, in the following phase, it makes no difference. In explicate control, if we're using, this is the test. So if we are using a variable, get bang is not possible there. Let's see, where's a get bang? Are we literally not handling it? Or set bang is there. Let's look at explicate assign. Right, we are converting this get bang into this, atomic variable thing, which is essentially the same as this. So in assignment position. Right, and in tail position, we're converting it to return this variable. So tail position is full expressions. We've removed complex operands. Honestly, I think this, I don't really know. I feel like this is fine to remove this marker at this phase. And I'm not sure what purpose it serves in the monadic form. And the, yeah, so, sorry, wrong window here. Preview, thank you. It exists in there, but you note that they're not like they have it here, but when they've converted L while to L mon while, you don't see any get bangs on this side. So I don't know that this change really matters in the grand scheme of things. I'm going to just restore that and make that not fail. And then let's go through and do the work to introduce the temporary variables, even though it's going to be a pain. So here at the top of the loop, we have to assign, or I'm sorry, sequence, and there's going to be an assignment of, there's going to be a temporary variable. I don't remember which one. I mean, we can talk our way through it, but I want to get to other stuff today too. So we may just like copy the variable names here. So in the loop, it makes sense that this is the first temporary variable actually. So we're going to have Adam okay, and then there will be the if inside that, and this will be temp.1. Okay, so then let's look at block 2, which is the body of the loop, and that's where the most of the temporary variables be introduced. We will be, we always process the tail first of a begin. So what we will see here is we're going to have another assignment. So this will be temp.2 of variable I.2, right? And then there will be, this is reading the variable temp.2. Okay. And then up here we have another set of sequences. Because this is adding sum1 and I2, and those are both mutable, we're going to assign. So we need to replace this one, so this is going to be temp.3, if I guess. C.variable sum.1. And that's going to be, an atom, like so. And that's going to have another sequence of assigning temp.4, right? So that will be the right-hand side of this plus. That's going to get I.2. Okay, and then we're going to put all of this yep, like so. Oh, one more. There, now it's inside. Okay, and then these are going to be temp.3, because that's what we assigned sum to, and temp.4. Okay, and then this is, you know, I'm going to put a comment here and say this is get bang sum dot one, and this is get bang I dot two. Yeah, and that's why we're introducing these temporary variables, and this is another get bang I dot two. Okay, let's see if our test passes now. It does not, so we probably have some issues with the numbering of temporary variables. So let's walk through it. Okay. So let's look at block 1 first. That is the same. Block 2. Okay, so this is temp 2 is assigned to sum1, and temp 3 is assigned to I2. Okay. I guess it's doing this in sequence. I thought it would go into the tail first, but so and I'm sorry, this is temp 2 and temp 3 for the arguments. Okay. Temp 4. Okay. So this is temp 4. All right, and up here in the loop we have temp 1. Right? That makes sense. That's the same. And comparing temp 1 to 0, go to block 1. Okay. Yep. Okay, so now I think we're correct. Yeah, we match up. I don't really think that it's important to dig into why the variables sequence that way. Why the temporary variable numbering sequenced that way. That's part of remove complex operands, and we could look at it in isolation. I mean, we could do IO debug here. Let's run that. Oops. And so here's the program that is output from remove complex operands. We have sum1 is that, I2 is 5, and then we have begin while loop. And here's that get bang. So temp 1, right? It got assigned in that order. The other way that we could approach this in the future is go ahead and look at what the output of our previous phases are, rather than trying to intuit the entire set of transformations. That's a distinct possibility of what we might want to do in the future. Okay. You know, I'm not immensely happy with this, especially those additional variables introduced where they're not necessary. But like I said, we know it's safe. So more tests. Okay, so we're going to do a test for while loops in explicate control. Okay, and we could, you know, that, like I said, the get bang only matters to remove complex operands. It does not matter to anything else. So we could remove that in this phase. We could choose to do that. And honestly, because remove complex operands is handling extracting that. This could just be atomic variable rather than get bang at that phase. I don't know that it matters. It may be a question we pose to Jeremy, the author, Professor Seek, and see what he says. Okay. So let's look at the book. We've done explicate control. I'm satisfied with the test there. Now we're going to select instructions. So we need to go and look at our pass here. And we're going to do like we've done in previous passes, where we alias this, and then we can wholesale replace the import while leaving the qualifications the same. So I'm going to change cif dot to c dot. Oops. And replace all those. And then we'll do the same for elif. For Pete's sake. Work with me here, editor. It's like honestly too responsive sometimes. Okay, so we're going to replace all of elif dot with l dot. And then what we can do is we can replace this with c loop, and this with this is L while. Okay. And the interesting thing here is that we're targeting I honestly want to replace this with x86, like an alias. Do you do it like that? Self? No. All right. I think we were... Let's leave this, and I think I want to replace... Let's find all the places where we use block. Use block, and we're going to replace that with x86 var if dot block, and it's going to have to be the constructor only, and we're going to have to be case sensitive. Oh, it's just this one place. Okay, so because what I want to do is I want to qualify this one too, so when we go and you change it later, that it's not going to be a problem. Okay, so yeah, let's just do x86 var if dot block, and then remove the unqualified version, and then we're going to say as x86, and we'll say x86 var if dot all the qualified calls to that. Okay, and we have no, I think we have no syntax errors here, but we are going to have some other problems, which we expect in exhaustive patterns. Okay, so here, select atom, and this is something that we're going to need to translate. So two small additions need to be are needed in the select instructions to handle C loop. First is to handle addition of void. We simply translate it to 0. So that's what they're talking about here. Void, we're going to translate to x86 immediate 0. Okay. Read may appear as a standalone statement instead of appearing only on the right-hand side of an assignment statement. The code generation is nearly identical to the one for assignment. Just leave off the instruction for moving the result into the left-hand side. So, so we're going to need, yeah, let's just go down here and have it add missing patterns. So, in the assignment, yeah, so we'll just do this and we'll leave off the move. And that's it. So the neat thing about some of these lowerings into languages with, when I say lowerings, I mean they have fewer abstractions, right? Assembly language, so the C-like language has fewer abstractions than the Lisp-like language. And assembly has fewer abstractions than the what am I trying to say? Than the C-like language. So really, that was not complicated. And it's interesting to see these, these incremental additions to our semantics of our high-level language actually don't translate to that much at the lower level. It's the transformations we have in between that remove or like, this is the job of the compiler, right? It pulls apart your high-level semantics into things that can be expressed with a lower-level representation. I think it's just fun to see, and like when you're at this step, you've got you really don't have that much more to do because you've handled all the other things except for you introduce void, right? Void is a value that can exist and can be constructed, and it just it's set to 0. Interesting, void and false are the same. But void is the nothing type, right? Like, and false is just, a condition was invalidated. Okay. So, select instructions test, we need to do this stuff like we did. Okay, so this one we just changed to C loop. If I can type. Oof. Okay, elif, we need to change to yeah, that's fine to leave. This needs to, let's find, oh, we had commented out all these tests, that's why it's complaining. So let's uncomment them. I think we were doing that so it would compile. And this is usually the phase that blows up. Okay. Right, so what I want to do is we're going to find all of the places in here. Oops. Yeah, that's fine. Where it says elif dot, and we're going to replace it with l dot. We're going to start with that. Okay, and then we're going to say a while as L. And let's see. Okay, so now we're missing a phase, which is after uniquify, we need to do uncover get. Sorry, I'm going to look at what we do down here. Parsing, shrink, uniqueify. Oh, shrink happens before. Okay, so let's get rid of the stuff we're not checking on. Okay, so shrink, then uniqueify. Okay, so shrink, then uniqueify, then uncover get, then remove complex operands, then explicate control. Okay. Are we doing that anywhere else? The only things that we need to test here are read statements. So, and void. Right, so let's make some tests for that. Okay. All right, let's do like what we did in the other ones. Let's do something like this. And this is oops. But I'm going to change the program. And let's get our parsed helper. Put that in this file. And I'm duplicating some things, but okay. So we're going to do a totally different program, and I'm just going to make it up. We're going to do, x is void. And then we're going to, I don't know, return 5. Like, this doesn't really do anything interesting. And honestly, this variable is never used, so it should be thrown away. But I want to show what these get turned into. So, and then we're going to have it explicate control. That's going to be our input program. And let's IO debug that, because I don't want to. I think what's going to happen is you're going to have like x.1, that's going to be the uniqueify. And then it's going to be, move 0 into x.1, move 5 into rex, and return. Or jump to conclusion. I think that's what it's gonna look like. So let's just go ahead and write that out. Okay. And that's blocks. Is it? All right, we did something like this. Let's go. Oh my. Let's go ahead and do that. So we're going to say base program here as the spread. And then what is the dang field? It's body. Okay. Yeah, so right, so we need a dictionary from list. Start is going to be the entry point. What's wrong there? I'm doing it as they do. Oh, 2 dots. Okay. Start, and each of these is a block. And then also has body. Okay. And that's a list of instructions. Okay, so we'll start with that. It's formatted, and we can start to put stuff in here. So what I expect to see is move an immediate of 0 into var of x.1, followed by a move immediate into register rex, and then there's going to be a jump conclusion. Okay, that's what I would expect for this. And then let's do p passed to select instructions should equal p2. And we can comment this out for now. Let's see what we got. Okay, so that did as we expected. You know, again, this is just debug output of the starting program, and that one was really easy to predict because it has only 2 expressions in it, really. Okay, so now we need a read statement, and I think that what we want to do is we'll use a modification of this. So this is going to have a begin read 5 or 2, and then we're not going to introduce anything that would cause a lot of these earlier phases to do a bunch of work. So what I want to happen is it calls readInt, it assigns x2, and then it returns 5. So again, we're going to having some we're going to be having some things here where, like, this program doesn't make sense. You would never write something like this. But we need to demonstrate that this, in effect position causes the function to be called and its value thrown away. So, all right, so I'm going to do something like this again, and we'll just rewrite the contents. Okay, so we're going to have start, and we're going to have we're going to have a call queue to read int. That's the first thing that should happen. Let's put our IO debug on here again, just so that we can see what this produces. And then we're going to have a movement of 2 to x1, and then returning 5. And let's see if we were right. Okay, so we have read statement, assign x1 to return 5. Yeah, so that's exactly what I expected to be generated, which is good. You love to see it. All right. And I don't think there's any other tests that we wanted to add. So let's go ahead and stage our updated files. And this is chapter 5.7. Okay. And then we get to the meat of it. And honestly, I say the meat of it. Register allocation is a thing that they spent a lot of time on early in this chapter. And it's basically, we're almost rewriting the thing. Almost. So let's read this section. And maybe what we can do is, rather than dig into rewriting register allocation, maybe we can update some of the things that are the foundational pieces. So what I mean by that is like our control flow graph. We can update that so that it's not required to be acyclic. Okay, so let's read this. So they discussed in section 4.2, the presence of loops means that control flow graphs can contain cycles. That complicates liveness analysis. Okay, recommend using the generic analyze data flow function that was presented at the end of 5.2 to perform liveness analysis, replacing the code in uncover live that process the basic blocks in topological order, right? So the analyze data flow is basically start with the empty set for each block, and then iterate on like computing the live before for each block until they all quiesce. So until they don't get anything new added to them. Like compute a fixed point. Right, so the first parameter G should be past the transpose of the control flow graph. That's just meaning that the arrows are going the other direction. And I think that when we did this originally, we used, let's see, we may have, it may just be in uncovered live. Let's look. When we found, yeah. So we added a vertex. So if it's not the conclusion on the jump, we would add a vertex, which may already exist for the label, the target, and add an edge from the label to the block name. So we were actually already adding them backwards. Right, so if we are here, we're in this block, then we then we did the, the topological sort at the end. So we will need to remove this topological sort. This is constructing the graph. And ooh, this looks, I don't know about you, but to me this looks ripe for a use because we have multiple callbacks here. Yeah, we may do that. Okay. And since we don't need to topological sort, we honestly, we would just use all the vertices, which are just the keys of the blocks. So there's not really anything like remarkable about this code, except that we are, rather than going from the current block pointing to the label it jumps to, we're going from the block to the label that it jumps to. I'm sorry, we're going from the label that's jumped to the block, which means that we've already got the edges going backwards in our code, so we don't need to change that, and we don't need to compute we don't need to do it forward and then compute the transposition, honestly, unless there's a compelling reason to have it in the opposite direction too. Okay. So let's look at our CFG here. The only difference is that we need to not expose topological sort. Well, we can expose it, honestly. It's just that now our graphs are not going to be cyclic. Or they're going to be acyclic. They're not going to be acyclic. They're going to be cyclic. Okay, so that's different. This top sort will return an error now. So like note here that if you call this, it's going to return an error nil. So this is how you would construct that Gleam type on the Erlang side. Which is okay. It means that I don't know if we need anything new in the graph, honestly. Let's look at this. Okay, so we'll look back at this function that they present, replacing the code and uncover live that process the basic blocks in topological order. Right, so for us, we had this build CFG order, which returned a list of the nodes. And I think that what we need to do is, let's look back at this section, 5.2. So they talk through like how the algorithm works in here and so forth. And okay, so this algorithm has 4 parameters, the control flow graph. So we need to keep the graph around rather than just consuming it and returning the topological sort. So I'm just going to copy paste this. We'll keep this function for now. And what we're going to do is call it build CFG. Of course, it's not used. But we're going to remove the top sort call. And this is going to return a CFG. And the type of that, remember it's generic. Our vertices are strings. what is our edge type? We honestly aren't specifying it here. We need it, but I think our edge type is nil, right? Okay, it's just complaining that it's never used. So what I want to do here is, rather than do it like we've done, we're going to take advantage of the use construct in Gleam, which lets you flatten these sorts of nested bits. So we're going to say, and this is like when you have a callback, right? So the last argument of a function is a function, like a higher order function. Then you can say use g block name block comes from dict.fold blocks and cfg.new. Okay, so there we've handled this bit, and now we can say use g block name, no, g instruction is list.fold, and we're going to fold over block.body, and the input is going to be cfg.add vertex g block name. Okay, and then the body of this function becomes the rest of this. So we just have the case. Now, again, it's complaining it's not used. So here we're saying, let me be clear about this, that this is, this step is construct a graph from the dictionary blocks. And this step is add vertexes for jump instructions inside the body of each block. That's what these steps are. We've just flattened them. So this is equivalent to this, but removing the top sort. It's just a different construction of it. And like, I think that sometimes there are good use cases for use, and there are ones where it actually makes things more confusing. This one borders on more confusing for me. However, since we have also previously built this, and we did it with pipes, like we could have, rather than piped this, we could have just put them inside as arguments, right? Like the pipe operator puts the thing on the left-hand side into the first argument of the function on the right-hand side. So we could have inlined those, and that would be more along what we have here. Regardless, I kind of like this. And especially since we added the comments here. So this, we can replace this with build CFG. Right, so now we've incorporated it into our old algorithm. And what we need to do next time, I think this is a good place to stop it, is to remove this. We're going to have to rewrite compute live after. And And maybe what we'll do is we will create this analyze data flow function. I thought that they were going to... Okay, so they have a generic work list algorithm for data flow analysis, and I'm guessing that this... Okay, so this is analyze data flow. We do have 15 minutes. Maybe what we can do is write a version of this that is translated into Gleam. And then we can finish it up next time. Yeah, let's make a function, and I'm going to, because we're just working in this one file, I'm gonna split like so we can see both the book and the editor. So we're gonna have analyze data flow. And right, so it's, what is it returning? It's returning a mapping of a block to a mapping of the block name to its live before set, which is basically what we're doing up here, but we were doing it in CFG order, and we don't care about the order when it's acyclic, or rather when it can have cycles. We have to do this sort of fixed point algorithm. Okay, so let's think through. I don't know what the return value of that is yet. Actually, it's going to be a dictionary of a string to set a set of location. Okay, so this is going to take this is kind of generic. So what they're doing here is they're saying, remember, like, this is about lattices. So bottom is the empty lattice, or the least most value in the lattice, which for us would be an empty set. Join for us is going to be set union. The question is, what is transfer? And I'm going to have to refer back to, okay, so function transfers that applies the analysis to one block. So that is transfer. What is it? Okay, so transfer takes the node and the input is find the neighbors for this node. Okay, so this is get me all the live before sets for the incoming edges, the blocks that are on the incoming edges, and just you're going to fold over them, unioning them together basically. So get the current mapping out of the dictionary, union them together, for all of the edges that may come into this, and then transfer again. The transfer function applies the analysis to one block, right? So the live before sets of the income from the other blocks are the live after set of this block, and then you compute what its live before set would be. And then update the dictionary. So we've kind of got this. We've got an algorithm that they've made generic, but we don't really need it to be generic in our case, unless we're going to use it somewhere else in this project. I don't think we need it to be. So this is going to take the graph, and I'm just going to call it G because it's our control flow graph of string to nil. Nil is the edges, the label on the edges essentially. And then we're going to use that with the set of blocks, which is going to be what is the type of input? Body, dictionary string to block. Okay. Right, because we need this. Like what they are doing is the transfer function has captured the set of blocks so that it can perform, like, analyze the statements in there and, iterating over them and so forth. So, like, we're still going to use compute live after or some form of it, but it's going to take, rather than right, so this was going through the block order, and the compute live after was using the blocks. So we will have something slightly different, because it would, like, go and look at what are the inputs. So, like, what are the destinations here, and union. It would do the union in there. So it's not exactly the same. Okay. Right, so it was getting the live before set of the other block. But what we're doing is we're saying, let's go around the graph, union them all up for it, and then use that as the input to this block. Otherwise, it's just, accumulating the before set. Okay. So right, so if we have the graph that we constructed here and the set of blocks, because we need to be able to get their code, then we don't need this transfer function. This transfer function is basically the same as the compute live after, but we're giving it the compute live before, we're giving it the live after set rather than having it constructed. Okay, so okay, so we're going to have a dictionary. We might need to have a like sort of inner function that we keep calling it. Yeah, I think what we're going to have is a we're going to build this mapping and this work list, and then rather than have this while, because we don't have a while in Gleam, what we'll do is we'll tail call, and that tail call will be like, if there's nothing in the work in the queue, then it's just going to return the mapping. Yep. So let's so this is going to have we're going to have an inner one, and what we're going to do is we're going to say let mapping is dictionary.new, and honestly that doesn't matter, except that what we're going to do is we're going to do this is saying what are the vertices of G, but we know it's the keys of the dictionary as well. So what we're going to do here is we're going to do, let's do dict from list. We're going to say blocks keys, right? We're going to get the keys, and then we're going to do list map, and we are going to return key and set an empty set, right? And then we're going to do dict from list. Okay, so now our mapping has this set of location. So that's what we're eventually going to return. And then our work list is going to be a queue. So we could, I'm not sure what we're going to do there, because we want to, maybe we'll just use list append. Yeah. It's not going to be efficient because, you know, you basically, it's bound by the left-hand side of that append, the complexity of it, because of con cells and also all of that. But so this is, we've constructed the bottom mapping. That's the most important thing. And then we're going to also, let's say, let work list is dict.keys blocks, and this is work list. We're gonna, yep, okay, this is basically the same. So now we can call G blocks, and I don't know, like I think maybe we would put work list first. Maybe not. The main thing here, and why I'm doing this, is we need to have a version. So what we're going to do is we're going to say analyze data flow inner. And it's going to have those arguments, and it's also going to have mapping, which is going to be a dictionary. It's going to be this type, right? And work list is going to be a list of string. And it's always going to return this type, the mapping. Okay, so the first thing that we do in this inner is the exit condition of the while, right? So if the work list is the empty list, then we return mapping because we have nothing else to do. Otherwise, we're going to try one node, right? Fine, it's unused. Okay, so now what we're going to do is we're going to need some functions in the CFG, and I need to finish up, folks. I'm really sorry. Here, let me get this formatted. We're going to need some functions in here, which are so they're only using in neighbors, and we could, I think, with the Erlang, well, let me see if I have those in Dash. We do have Dash. Okay. Sorry, folks, this is going to be a little bit small, but we have digraph in Erlang is what we're using for that. So we can get, you can do in neighbors and out neighbors, right? So we don't need to transpose it. In fact, it doesn't even look like there's a function for transpose. And how is it able to do that? Well, it's backed by ets. So in neighbors is like pattern match on this field versus that other field. So yeah, versus out neighbors. So the implementation is actually quite straightforward. Okay, so what we'll do is we're going to need in neighbors is going to and it's going to take a vertex v, and it's going to return a list of v, and the same for out neighbors. So let's see what in neighbors returns. Right, so that returns a list of vertexes. Okay, so we're going to do the same, right? And let's just, we're going to export in neighbors and out neighbors. And in neighbors, G and B is just going to be digraph in neighbors, G and B. And out neighbors. The reason I've done this with FFI is partly because Gleam requires it, but also what we would like to do eventually is have FFI to JavaScript. And then we can run our whole thing in the browser and just implement these functions, again, binding to a JavaScript library for graphs, which I have, like, I think bookmarked in my browser. So, so that's all we need to do for that. And now we have in neighbors and out neighbors in our control flow graph defined. And so now, let's go ahead and do the last bit, and then I'll wrap up for the day. Okay, so now we're in the body of this loop, essentially. This inner is the body of the loop. So wherever they use the transpose of G, we want to call in neighbors. Where they use the regular G, we want to call out neighbors. Basically what we're doing here is saying, hey, if I changed, if my before set changed, then I know that the things that draw from my live before set need to be recomputed. That's what this analyze data flow algorithm is doing. Okay. So what we're going to do is eventually what we're going to call here is we'll go ahead and make a function called transfer in here just for consistency. And we'll set it with a to do. And this is going to be, it's going to take the block. Let's see, what's the live after? So it's going to take a list of instructions. And it's going to take the live after, which is going to be a set. And it's going to return a set location. So this is really just compute the live before. So it's the essence of this other algorithm without handling the jumps explicitly. And it does not care about. So what we need to do to get to that point is we need to go. We're going to call it input, and we're going to we're going to take the in neighbors of, so G is the node, right? I'm going to pipe here. We may want to flatten this later. So give me the in neighbors, and then we're going to list fold set.new and give it so I'm going to call this neighbor. They call it pred. Fine. Predecessor, pred for predecessor. And the accumulator is going to be the state. They're calling it state. So I'm just trying to keep consistent with them, even though I don't always like it. So we're going to set union actually we don't need to do we're going to get from the blocks the lots of pipes. It's going to get ugly. I'm sorry, folks. So we're going to get the block, or not from blocks. We're going to get it from the mapping, right? Because that's what we want. And this is going to be result dot unwrap or yeah, we'll do lazy unwrap. Set new. And then we'll pass that to set union with the current state. So basically we're just trying to fold over the okay, so now it's just saying it's never used. So what is the type of input? It's a set of locations. That's exactly what we wanted. So this is the input for this block. And so then we need output is going to be transfer, and the live after set is going to be input, right? Output is, so what we need here is the instructions from that block. So we'll do instructions are dict dot so we'll do block.body as the input there. Let's let assert OK. And now we have the output. And then what we can do is say if it's so that's recomputing the live before set. Why don't we do this with a case? Well, let's do let assert OK. Previous is dict.get on mapping of the node, right? So this is what the set was before. And then if output equals previous, And then we know it didn't change, so we don't need to enqueue its neighbors. If that's true, then we just call analyze data flow inner with G, and it didn't change the mapping, right? So the blocks are unchanged still. The mapping is unchanged. And now we have the remaining work list. Okay? If they aren't the same, then we need to, we're going to call analyze data flow inner again. G and blocks again are unchanged. So we're going to insert into mapping for node the new output. Okay, so that's the first thing that changes on this next iteration. And then the work list, we are going to list append work list, and we will say CFG out neighbors of node. Okay, so hopefully that is clear what we're doing here. I suspect that this particular thing is not going to be great, and what we could do is, for instance, use a queue from Erlang, and we could use a queue from JavaScript. And JavaScript, obviously, it's fairly efficient to concatenate two arrays and use the front of the array and slice them off. But in functional languages that are immutable, like Erlang and Gleam, typically what you do is you enqueue onto, you have a pair of lists and you enqueue onto one, and then when you dequeue, you empty it, you empty off the first list, and when that's empty, when that dequeuing is empty, then you swap them and reverse them. So you get you get efficient appends because they're appending on the front of the list for the input, and they're dequeuing off of the front of the list for the output. But then when you exhaust the output, then you flip them and reverse them, and then you get them in the correct order. The thing is that I don't know if this particular queue data structure has a multi-append or whether you need to do something like this loop. The interesting thing here is that it doesn't really matter what the order of these are. It's just that, hey, you need to recompute them. So, okay. It's also got a bunch of funky aliases for the same thing. I wish they'd picked one. So inserts the item at the rear of the queue. You can join two queues together. I guess that's what you would do. I don't know that it's any more efficient than this list append, honestly, in the end of it. Okay, so this is a good place to stop. I went way over my intended time, but we got this basically implemented, with the exception of transfer, which is going to be a rework of the compute live after, and then we'll do that next week, hopefully. So thank you for attending, and thank you for continuing to watch my content on YouTube, and like and subscribe, of course, as they say. Otherwise, we'll see you next time. Take care.